Section 4.2, page 2. First, let's talk about a couple of pieces of information. Assume that a biker travels 45 kilometers in 3 hours, and you're asked what their average speed is. So we're going to take the total distance divided by the amount of time traveled, and on average, this biker was traveling at a rate of 15 kilometers per hour. Now, does that mean that they had to go 15 kilometers per hour at least once during the trip? Yes, it does mean that, because they had to have gone that either the whole time or at least a little bit faster than it at some point to make this be the average, and therefore they would have had to have hit that speed. Now, the question is, did the biker have to also have gone 17 kilometers an hour at least once during the trip? Well, I mean, they might have, but the 17 isn't required to be true, right? Even if they started from a stopped point and had to speed up, maybe they only ended up going 16.9 for a significant distance of the trip until the average was 15 kilometers, 0.9. Per hour. The thing to recognize when I'm mentioning over here is this speaks to average, which we know is slope of a tangent line, and the rate that the biker was going, which is a derivative. And basically, at some point, they had to equal a value in the range. And so that's what we're going to tie in now. We've talked about Rolle's theorem. That's a special case for the mean value theorem, but we hadn't discussed the mean value theorem. It starts off with the first two conditions of Rolle's. Let f be a function that is continuous on a specific closed interval and differentiable on that open interval. But unlike the special case of Rolle's, we don't need f of a and f of b to have equal outputs. We just know that there is some number inside of that range where the derivative is equal to basically the slope of the endpoints. Now, in Rolle's theorem, because the output equaled the same for both inputs, that's why this equaled 0. But they aren't necessarily needing to be equal. But if you recognize the formula on the right, this is just the slope of 2 points, which in our case is a secant line. And f prime is notation for a derivative. So a derivative is a slope specifically of a tangent line. So we've got this picture over here. I've got these two ends of my closed and open interval. They happen to have different outputs, which is fine. But anytime I have 2 points, I can connect them with a line, and that gives me a secant line, which has some particular slope. We're saying somewhere in here, could have been way over here, doesn't really know until we do the math, there is a point C that is going to have a tangent line, and that particular tangent line is parallel to the secant line. Remember, parallel lines have the same slope. So the slope of the derivative equals the slope of the secant. In terms of how we use it, it's to prove lots of different situations in mathematics. We'll begin with example 3. Verify that this given function satisfies the mean value theorem specifically on the closed interval from 1 to 4, and then find all values C that satisfy the conclusion of the mean value theorem. So first we need to verify the mean value theorem is met. We said we need the function to be continuous on a closed interval. The given function is continuous everywhere except for when the denominator is 0. The denominator will be 0 when x is -2, but -2 is not inside our interval, so therefore the interval from 1 to 4 is continuous. Also, the function needs to be differentiable on the open interval. So we need to find the derivative of x over x plus 2 using the quotient rule, where we take the derivative of the top with the denominator untouched, then we take the derivative of the denominator with the top untouched, and square the denominator. So combining like terms leaves us with just a numerator of 2 and a squared denominator. Now, if this is the derivative, it does not exist when x is -2 because we would be dividing by 0. But again, -2 is not in our open interval. So therefore, all of the conditions of the intermediate value theorem have been met for this function on the interval 1 to 4. Now we're asked to find all of the values c. The mean value theorem states the derivative of some value c is equal to the slope of the tangent line of the inputs. So I've just copied that formula here. So if our closed interval is from 1 to 4, then A is 1, B is 4, and we can plug those into the slope equation accordingly, where 4 minus 1 is just 3. But to find the outputs, we need to go not to the derivative formula, but to the original formula and plug a 4 in for x and a 1 in for x, so that I end up with 4/6 minus 1/6, recognizing that 4/6 can reduce to 2/3. And therefore, when I go to subtract 1/3, I have like denominators and can just subtract the tops to get a positive 1/3. Keep in mind that that was just the numerator, so I have the numerator divided by the denominator, so that 1/3 divided by 3 is really like multiplying by 1/3, so we have 1/9. On the left side, we have the derivative of c. We had already found the derivative when we proved the mean value theorem, so all I need to do is swap that x with a c. And now I have 2 over the sum of c plus 2 squared is equal to 1/9. I'm going to go ahead and cross multiply my denominator times my numerator and the other numerator times the denominator, so that I will end up needing to take a square root on the left to get c out of the squared product. And of course, I just multiplied 2 and 9. When we take a square root on the right, it's plus or minus. And if I was to subtract this 2 over, I'm going to have a -2, where once it's with the minus square root of 18, and my -2 where it's once with the plus the square root of 18. You can first of all just tell this is going to be negative because I have a negative number minus something else that does not appear. Oh, actually, I guess it could be, depending on the value of it, I guess, may seem deceptive, but we're not going to get a negative, right? But we could get out a calculator, and this negative value is not in our interval from 1 to 4. But when I get out a calculator, -2 plus the square root of 18, I get positive 2.2 something, which is inside my value, and therefore I have now found the only c value in this range.